electric field component exists. So uh, to be able to get the solutions, we said that because these are the unique components for either of the modes, we would solve for these two modes present here. We will solve we'll solve the Helmholtz wave equation in either Ez or Hz, and from there we will derive what the other components are. So in order to do that, basically we had to go back to the Maxwell's equations. We took the Maxwell's equations, either the Faraday's law del cross E is minus j omega mu h, and hidden within this single equation, there are three equations, each in a different component of the field, x, y, or z component. And similarly, we took the Ampere's law del cross h is equal to j omega epsilon E, and hidden within that, there are three other equations present. What we want to do is that if we know the value of Ez or Hz, we want to be able to calculate what a specific field in x or y direction is, Ex, Ey, Hx, or Hy. So we want to write equations of Ex, Ey, Hx, Hy in terms of Ez and Hz. So by taking one equation from here and another equation from here, we can write an equation in terms of Hx. So if I take these two equations, they have a component of del Ez by del y and del Hz by del x. So Ez and Hz are the ones which I'm going to solve with Helmholtz wave equation. So by taking a component here, we can combine these two equations to write a single term in, in terms of del Hz by del x or del Ez by del y. Remember, for TM modes, only only one of these two components would exist. If it is a TE mode, Xn would exist, but Ez would be zero. If it is a TM mode, Ez would exist, Hz would be zero. And similarly, we can derive four equations in the four transverse components of the field, E and H, in terms of the longitudinal component. Again, remember, these four are four or five fields. The five fields, the TE mode and the TM mode, now are going to have five fields. It's as if there are five different hands of the same mode. All these five components are part of the mode. It's not that the mode is if each of them is a separate mode. All of these are a separate component of the mode, separate hand of the mode, if you will. As opposed to parallel plate waveguide, which had three components, rectangular waveguide has five components of the field, four components in the transverse direction, and one component in the longitudinal direction. Considering this, we had then considered a rectangular waveguide, and we had said that let's look for the TM mode. We said let's start with our assumption that the mode is TM, and we are looking for a mode which is propagating in the Z direction. So it is going to have E minus gamma Z kind of a term in it. But its amplitude is going to vary in X and Y. Again, remember, the field has to be zero at the bottom. The field has to be zero here. This Ez field is traveling in this direction. This field is parallel to the bottom conductor and is parallel to the side conductor also. So the parallel boundary conditions have to met. So the field has to be zero here, the field has to be zero here, has to be zero, and has to be zero on all those four walls of the waveguide. Because of that, because of these boundary conditions, we realized that the field can only take a sine wave depending on the origin we have. So, and it's going to vary as a sine in x direction, and it's also going to vary as a sine in y direction. So the field is going to be now dependent on whether or not a Wilmot form of this particular case. Again, remember this field is pointing in z direction, but now has amplitude variation in x and an amplitude variation in y. And the values of m and n can take their integer values from a 1 onwards. What does m mean? M means how many lobes do we get in x direction? So within this waveguide, if I was plotting the field distribution would be some kind of a contour. And if I take a cut across this in x and y, well, if the answer is like that, it's one lobe. If the answer is different than that, let's say this is 0, then this would be two lobes. So for this, for the first lobe, m would be 1. If it is two lobes, m would be 2. How many lambda by 2's can you fit within that x direction? Similarly, n means how many lobes can we fit in y direction. If I took a cut of the field in the y direction, how many different lobes would I have? How many different peaks and troughs would I have in that y direction? Based on the relationships we had derived before, the various other components of the field, the transverse components of the field, turn out to be of a different form. And let's quickly understand a couple of physical things. If I take a look at EX form, if I take a look at EX form has sine term in the y direction, but it has cos term in the x direction. Why is that? Well, what is EX? EX is a field which is pointing in that direction. This field is so this field is parallel to the boundary conditions in the y. It's parallel. So this field has to be 0 here. This field has to be 0 on the top. But this field is perpendicular boundary condition to the side walls. Because the field is parallel to the top and the bottom conductor, the electric field has to go to 0 at the top and the bottom conductor. And the only way that can be 0 is by sine. Whereas perpendicular boundary can still exist. And what happens with the perpendicular boundary, what happens at this boundary over here is that the field is going to induce some charge. And the magnetic field, if there is any presence of the magnetic field over there, that magnetic field is going to start to take that charge and is going to start to flow that charge as some current. So this field This sine function basically is telling you that the field is in x direction, so in the opposite direction towards it, it has to maintain the boundary conditions that the field has to go to zero, and thus I get a sine form in front of there. Ey field, on the other hand, would have a sine function in the x direction and a cos function in the y direction. Now, other thing you would notice is that if I look at Ex field, the variation over here, that variation is very similar to Hy field. Ex field has a variation of cos in x direction and sine in y, and Hy field has a variation of cos in x and sine term. And similarly, Ey field has a very similar variation as we see in the Hx, the opposite field towards it. Remember again, the Poynting vector S, which is how the power density flows, is E cross H, and the average Poynting vector is half of real of E cross H. Sorry. And notice here now that if I take a look at this term and this term, I would get x cross y, and I have two negatives that would become positive, but I have x cross y which is going in z direction. So these two components have power flow in positive z direction, and similarly, if you notice these two components, this is y cross x, again E, the direction of E cross the direction of H tells you the direction of propagation. And if you notice here, y cross x is minus z, but there is only one minus in this term, so that becomes plus z again. So this is also in plus z direction. So it's telling you that the total power flow which is now going through my waveguide is going in two different pairs. There is one pair which is a pair of Ex cross Hy, and another pair which is Ey cross Hx. That's how that power is going to come. However, all these are the same arm, or these are the different arms of the same mode M and N. So all these are traveling with the same propagation constant, and all these are traveling with the same velocity. And the propagation constant we had seen was basically given by this term over here. And if you notice, this is almost very similar term to what we had seen before. Previously, when you had the term for parallel plate waveguide, this term which I put in yellow was not included. The propagation constant was just j square root of omega square minus mu epsilon minus m pi by a square. Now, so basically it was said that the propagation term was reduced by the confinement you did in the direction of confinement. In that specific case, it was the confinement was in the y direction. Now, because we have confinement in the x direction too, we have confinement in another direction also, the propagation constant is reduced by the same amount as before. So this equation, if you look at the propagation constant equation, that is in principle to very similar to the parallel plate waveguide. In parallel plate waveguide, there was one directional confinement. So we saw m pi by a square showing up there. Now we have two directional confinement. So we add another effect of that. So it is n pi by b square. That part is again subtracted. That term is added up now. If we go to three directional confinement, which we will do in the last unit, which is called a resonator, you would see that the propagation or the resonance terms would be now another term would be added, which would be some j mn l pi by c square. So these terms are very similar in all these geometries. Also, when we looked at the TM board, we had seen that these components cannot exist. That anytime m is equal to 0 or n is equal to 0, those two modes cannot exist. Why? If either m is equal to 0 or n is equal to 0, Ez goes to 0, and not only that, every other term goes to 0. Every other term is dependent on Ez. If Ez is equal to 0, then those terms do not exist. So if either of m or n is equal to 0, the sign term goes to 0, so there is no mode present. So the lowest order TM mode is going to be 1, 1, which basically means there is one major lobe, one peak in the x direction, and one peak in the y direction. So it's a mode which is almost looking like that of a semiconductor laser or a laser pointer. If you have seen, if I shine a laser pointer onto a wall, you have a peak in the center and it decays outside. It's a mode which is almost looking like that. It is going to have one peak in the x direction cut and one peak in the y direction cut. That is the lowest order mode. And the cutoff frequency of every mode, again remember this term is again looking very similar to what you had seen for parallel plate waveguide. It was just the term in the front. Now because there is a confinement in the other direction too, the cutoff frequency becomes second term is added to the cutoff frequency. So this is what we have seen for the modes so far. Let's look for. Do you have any questions on what we did on Friday on this review? Any questions before we start the maths for the TE board? All right, let's start the solution for the TE board then. And again, we are going, the geometry is exactly the same. I have a rectangular waveguide with, going to call this as 0, A, B, and we are propagating the field in the Z direction. But because it's a TE, we know that Z is going to look at, we're going to see at Z, it's going to have some function at Z xy E minus gamma Z. We are still looking for the solution which is propagating in Z direction. By Helmholtz wave equation, is very similar to what we saw in TM mode, except now instead of having E, it is going to have H plus H square Hz xy is equal to 0. These are the solutions which I have to look for. Again, we're going to call my Hz xy as a function of xx and yy. And similar to what we did for TM mode, we're going to get an equation which is 1 by x d square x dx squared plus k square x is equal to 0 and 1 by y d square y dy square plus k square y is equal to 0 and k square x plus k square y is going to be equal to h square. This is exactly the same maths we did on Friday. All we do is we substitute this in xy. So you get a differentiation in terms of x and a differentiation in terms of y. We divide the whole equation by xy, and then you get two parts of the equation, one part which is only varying in x and the other part which is only varying in y, plus the constant x square. So each part, the part which is varying only in x should be a constant, the part which is varying only in y should be a constant, and the sum of the constants should be 0. So this is basically exactly, nothing has changed so far with respect to the calculations we did for TM mode. The only thing which has changed is instead of having the electric field, we have the magnetic field. Now comes the question, what are boundary conditions? And this is where we have to think a little. Remember for TM mode, when we were calculating TM mode here, life was quite easy. Why? Because we were having an electric field in Z direction, so we had an electric field Ez, and that electric field was parallel to the two conductors, parallel to the bottom and the top conductor, and parallel to the side conductors. And parallel electric field boundary is very, very clear. Parallel electric field boundary has to be 0. There cannot be any ifs or buts about it on a conductor, right? Now, for the same condition, for the same geometry, we have a magnetic field which is in HZ direction. And the parallel magnetic field can exist, and the parallel magnetic field, if it exists, all it does is it creates a current, a surface current on the plate which is perpendicular to the direction of the magnetic field. So I cannot say that Hz is going to be 0 at the boundaries. That cannot be true. I cannot it can take any value. Oops, sorry, any value, and will generate a surface current. That's the thing which HZ does. So I cannot tell what value HZ is going to take. So now I have to get out of that conundrum. To get out of that conundrum, let's go back to the fields. Let's go back to these equations which we had here. And remember, what I can guarantee is what happens to the electric field. If there is an electric field which is parallel to the boundary, then then that electric field has to be zero. That is what I can guarantee. I can't guarantee what values H can take. I can't even think of what values H can take. Whatever value H takes at the boundary is going to be supported by a surface current which would be generated on the conductor. So to get out of the conundrum, to figure out what my boundary conditions are, I should go and look at what happens in the electric fields. Ex electric field, which is in the x direction, is going to be parallel to the top and the bottom conductor, and Ey electric field, which is vertical, is going to be parallel to the side conductors. So I know for sure Ex and Ey in a TE mode have to be zero at the two boundaries. And for a TE mode, what does exist? Well, this term doesn't exist for a TE mode. This term doesn't exist for a TE mode. So what does Ex depend upon? Ex depends upon my derivative of H z with y. It depends upon the derivative of Hz with y. And what does Ey depend upon? It depends upon the derivative of Hz with x, the opposite direction. So Ex depends upon the derivative of Hz with y, and Ey depends upon the derivative of Hz with x. Well, but Ex has to be zero at the boundary, which tells you that the derivative of the magnetic field has to be zero at the boundary. So I can't tell anything about the value the magnetic field will take, but because of these fields which are dependent upon this magnetic, and these fields have to be to zero at the conducting boundaries, I can tell what the derivative of the field is going to do. So effectively now, my boundary conditions are del xz by del y has to be zero at, and this is the condition where, because my Ex has to be zero, and del hz by del y has to be zero for y is equal to 0 and y is equal to b. And remember, I have a rectangular waveguide. My Ex is in this direction, and Ex has to be 0 at here and up there. And the derivative of my hz with x has to be 0. Why? Because ey has to be 0 at x is equal to 0 and x is equal to a. These form the boundary conditions for my waveguide. Any questions on the boundary conditions? It's important that you understand these boundary conditions well. Any questions on the boundary conditions? Any questions? Is it clear? Again, just to repeat, the I cannot judge what the value of the magnetic field is going to be at the boundaries. It can take any value it needs to take because it is supported at the boundary. However, because the electric fields are dependent upon the derivatives of the magnetic field in z direction, in the longitudinal direction, I know that the electric fields have to take a value of 0 and at the boundaries. And because the electric field has to take the value of 0 and electric field is dependent on the derivative of the magnetic field, the derivative of the magnetic fields have to take a value of 0. These boundaries where the derivatives are included are known as uh, Dirichlet boundary conditions. Mathematically, they are known as Dirichlet boundary conditions. And they are named after Peter Gustav Dirichlet, who was a mathematician in the 19th century. So now, the solutions we are looking for are the solutions of the wave of the equation, sorry, d square x dx square plus kx square x is 0 with boundary condition that dx by dx is 0. Again, the derivative of that is 0 at x is equal to x is equal to 0 and x is equal to a. And similarly, we have the other equation, the others using the separation of variables, d square y plus dy square plus a square y is equal to 0 with boundary condition that dy by dy is 0 at y is equal to 0 and b. Again, the first form hasn't changed at all with respect to the TM wave. This is exactly the same form. Should have the same solution. Again, it's telling you that I have a function. I take its derivative twice. I add it with some constant to the function, and I get a 0. So it has to be a sinusoid or a cosine function. So I know that x has to be some constant a prime sine kxx plus constant b prime cos kxx. And because this is 0, dx by dx is 0, and x is equal to 0, I take the derivative. Dx by dx is a prime kx cos kxx plus b prime kx or minus b prime kx sine kxx. And at x is equal to 0, this becomes a prime kx is equal to 0. So the sine function doesn't exist. It should. I didn't even need to do this math. You could have easily said, hey, the cos function has derivative which is slope which is 0 at x is equal to 0. If I plot a cos function, you have a cos function which goes like that. The slope here is 0. The slope somewhere else would be 0 too. So that's how things would fit now. So sine function does not exist and only the cos function exists. Similarly to this, the y function also would only be of the form of a form of cos function. So it's telling me my xx can only take a form of some constant cos kxx, and y would only take another form, let's say c prime cos of ky y. Now let's do the boundaries at x is equal to a. Again, dx by dx at x is equal to a has to be 0, which becomes minus b prime kx sine kxx or sine kxa has to be equal to 0. That can only happen if sine kxa is equal to 0, or again kxa is equal to m pi. Nothing has changed here. Kx is m pi by a. Similarly, applying boundary condition at y is equal to b due to y is equal to b boundary condition, my ky has to be of the form of n pi by b. Here again, m can take, for the time being, mathematically, m can take values from 0, 1 onwards, and n can take values from 0, 1 onwards. Mathematically, it can take those values. Physically, we'll see whether it can take the values, all these values or not. So looking at the solution, it tells me my Hz for the TE mode has to be, is of the form of some constant. When I multiply two constants, it's still a constant, so I'm just going to define another constant. Sorry, my computer is giving me problems. It's going to be some constant h naught cos of m pi by a x sine of n pi by b y. So it can take these values over like that. From these equations and then applying what we had seen before, applying these terms over here, we can now get the values of the other four fields in the transverse direction. So, so this is your longitudinal component, various transverse components will now be given by, you can do those derivations. It's simple derivatives. Ex, xy, that's the amplitude variation pointing in x direction, j omega mu by h square n pi by b h naught cos of m pi by a x sine of n pi by b y. Then I have ey y is minus j omega mu by h square m pi by a h naught. You will have a sine of m pi by a x, and then you'll have sine of n pi by b y. And similarly, we can write the fields in hx component, which would be gamma by h square, m pi, x component would be m pi by a, h naught sine of m pi by a x cos of n pi by b y, and you have hy xy would be minus gamma by h square n pi by b h naught cos of m pi by a x sine of n pi by b y. Later on in tomorrow's class, we will try to understand what these various things work, what these various things mean. Now let's see what all components of the field can exist. Previously, we had seen that if one of the components was 0, m or n was 0, then the other component cannot exist at all. I have an error here. It was confusing me. That should be cos. Should have caught me on this. Alright, so now when we look at it, let's see what all components can exist. Will 0, 0 exist? Well, if both m and n are 0, if m is equal to 0 and n is equal to 0, hz exists for sure. It's just h naught, some constant h naught. But because both of them are zeros, one sign will not exist on ex. So this term will not exist because of this term over here. This term will not exist because of this term over here. Hx will not exist because of this term over here. And hy will not exist because of this term over here, if both m and n are equal to 0. So yes, there is some magnetic field pointing in the y direction, in the z direction, in the longitudinal direction, but there's no other transverse field present. And if there are no transverse field present, there's no wave. It's the transverse fields which are creating the wave, and part of that energy sometimes goes into the z direction. But in this case, TE00, all transverse components of the field go to 0. No wave exists. So TE00 cannot exist. What about 10? Again, if I look at TE10, uh, if I take a look at TE10, HZ HZ will exist for sure. But now what will happen is, because the n is equal to 0, E Ex doesn't exist, but Ey does. Hx doesn't exist. Sorry, Hx exists. Hy goes to 0, but Hx exists. So in TE10, you have three components to be present. You have Ey, Hx, and Hz. Similarly, TE01, you'll have, instead of Ey, you'll have Ex in pointing in x direction, Hy, and Hz. So it's telling me TE M0 and TE0N modes exist. This is different from TM. Remember, TMM0s and TM0N modes will never exist. However, TE10s, TE20s, TE30s, TE01, all these modes would exist. If A is greater than B, then TE10 will have lower cutoff frequency than TE01. This becomes the dominating mode. If you look at the cutoff frequency equation hasn't changed at all. The value of again, remember the condition is that kx square plus ky square is equal to h square. That hasn't changed. H square was omega square mu epsilon minus gamma square. So gamma square is omega square mu epsilon minus ax is m pi by a square minus n pi by b square. And cutoff frequency happens when gamma is equal to 0. So the cutoff frequency omega cutoff frequency, come on, sorry, my computer is giving me problem. Omega is going to be given as similar to what you had seen before, 1 by square root of mu epsilon square root of m pi by a square plus n pi by b square. This formula has not changed from Tm. This is same form as Tm. The thing which has changed is in Tm, m or n cannot take a value of 0. In Te, either m or n can be 0 at a time. Both cannot be 0 together, but one can be 0 and the other can take any value it wants. So I was plotting the cutoff frequency. FC would be given by 1 by uh, 1 by 2 pi 2, yeah, so 1 by 2 a square root of mu epsilon, sorry, my mistake here, cutoff frequency would be very similar to the Tm and would be 1 by 2 square root of mu epsilon. I've taken the pi outside of the terms so that I can cancel the pi in omega with the pi I have in the terms. M by a square plus n by b square. So now what you're going to see is the cutoff frequency for 1,0 mode is going to be given by 1 by 2 square root of mu epsilon 1 by a Substitute just m is equal to 1, uh, n is equal to 0, and the cutoff frequency for 0, 1 mode is going to be given as 1 by 2 squared mu epsilon 1 by b. If a is greater than b, fc 10 is going to be less than fc 01. If a is equal to b, which is a square waveguide, was a question asked last week, then fc 10 is going to be equal to fc 01. The two modes are going to be degenerate. Let's assume a is equal to b, and if I was plotting the frequency plots, you're going to get a cutoff here, which is fc 10, and below that cutoff, in this shaded region, no guided mode is allowed. In that shaded region. Then go to another value, which is going to be sorry, sorry. Just a second, please. My computer is giving me some. It's not letting me write. No. Just a second, please. All right. Hopefully it'll work. If I go to another mode now, I'm going to get fc 01 present there, and this is where the second mode which can exist. Now what happens is in the shaded region here, over here, only TE10 exists. 10 exists in that region. So in this shaded region between FC10 and FC01, the waveguide is only allowing one and one solution to go through. No other solution is allowed. No other distribution is allowed. There is only and only one distribution allowed, which is traveling with its own phase velocity within these two components. I go further up, and when I reach the next point, I'm probably going to get FC11 term show up, or I'm going to see FC20 depending upon what the values are. If it is FC11, let's just that depends completely on the values of A and B, which one will show up first, FC20 or FC11. For the sake of argument, let's assume that FC11 shows up before FC20. Now, in this region over here, TE in that region, TE01 and TE10 both exist.
No, sir. Everything is clear, sir.
All right, then we'll sit tomorrow. I probably have to clean up my computer. I think it's running out of memory, so when I'm writing, it's giving me a lot of problems. But I will see you tomorrow. What we'll do is we will look at these field distributions. What they do they mean? We'll look at a few field distributions of TE and TMs. Uh, we'll try to physically understand why TE can exist, but TM has a higher code. Like why does that physically happen? Mathematically, we know now that it happens, but why physically that happens? We'll take a look at that tomorrow. And then by Wednesday, we should have finished completely this this part of the course. All right. Good. Have a nice day for the rest of the day, and I'll see you tomorrow if you have no questions.
Have a nice day too, sir. Thank you.
All right, bye.